Okay, I'm back again. My first video, which I'm currently downloading now, it says it's going to take 30 minutes to download to YouTube. Anyway, just a quick overview of the first video. We're going to start with the smallest stuff, the smallest things that have mass. The center whiteboard equals the space atmosphere. And I finished off with, do you think things with mass actually can physically touch? Okay. And that was my question I'm looking for answers for at the end of my first video. So picking up from there, here I left off. We're going to pick up right where I left off. If I can find the Sharpies. The Sharpies. Okay, so at this point here, I'm going to continue down a path knowing that it may be wrong, but it's the one I feel right about. So I'm going to continue down that path. So we're going to stick with things don't touch. Okay, until someone can prove me wrong, we're going to stick with things don't touch. We're going to talk more about what's happening here. Okay, so I'm just going to erase this other stuff. We'll leave this picture here so I can expand on that. All right, so if you can't see it here, I'll just move it a little closer. If things can't touch, the space atmosphere around it gets stretched. Okay. Now you have the mass, you have the gravity bubble of two objects now, instead of just one, and it's being stretched. It's being stretched in two ways now. It's being stretched by the mass of each object has their own gravity bubble, but since they're close to each other, now it's being stretched even more. Okay, so where you might have had two beach ball sized gravity bubbles. Well, let's volleyball, soccer ball sized gravity bubbles. Okay, if you had two soccer ball sized gravity bubbles, and now they're touching, you wouldn't have the same mass as two soccer ball sized gravity bubbles. It would be a little bigger because you're stretching even more. These two objects are now trying to get closer, and that stretches the gravity bubble even more. Okay, now that's up for discussion too. Okay, is the gravity bubble stretched even more? And that could be a question that I'll write up here. Alright, let's just do this here. Is the gravity bubble stretched more when two masses meet? Okay, there's another question. And again, you can contact me there or here, wherever you want. If you have a thought on this, I'd love to hear it. I'd love to hear it. Okay, so I'm going to expand on that they don't touch. And what was that? Is the gravity bubble stretched more? So that's an entirely different question than that one. Is the gravity bubble stretched more when the two masses meet? Okay, that's not going to concern me right at this point. I believe it is, but it's not going to concern me right at this point. So right now we have two objects, okay? Now that they can't touch, it's got a distinctive, what did I call them? Tendons. It's got distinctive tendons now. It's got an area that's distinct where it's the stretch is the strongest, okay? And that's in between. And it expands out from there. Now obviously we can get other masses that come in. This has already got a spin. We're getting into the physics of things now. Well, we've been into the physics of things the entire time, but I don't know the technical terms. So obviously we can keep expanding this picture. If another object of mass, you know, bigger mass. Sorry about my whistling. Bigger massive object, you know, with a bigger gravity bubble comes into contact with these two. Now none of these can, if they can't touch, okay, so what we'll end up with here, I just closed that, is something like this, okay? Maybe it'll be something like this. Now I have to redraw my gravity circle there, my gravity bubble circle, okay? So now this is where it can kind of get interesting. So we have this bubble, we have this bubble, and then we have this bubble, okay? Where nothing can meet. So we're going to have an attraction like so, okay? But it's still only being stretched. It's still only being stretched. Okay, now we already know that there's also movement for these. There's also going to be a spin. For these things to come together, one of them has to be moving. And because space atmosphere does not slow things down, it's not going to stop moving. It's not going to get tired. It's just going to keep moving. There's nothing to slow it down. It's like I said with the baseball, you know. And if I throw a baseball in space and it doesn't come in contact with any gravity, it's just going to keep going at the same velocity until it comes in contact with some gravity. It's just going to keep going. Okay? And that would be an awesome one to prove. But in order to properly prove that one, we would need to be pretty much out of our galactic gravity shell. So yeah, that's a little bit of travel time to get there to prove that one. I mean, it would probably work. It'd probably work in our solar system. You know, you leave the planet Earth, you get to a certain distance out, and you throw a baseball. And what's going to stop that thing? You know, gravity is the only thing that'll stop it. Gravity is a weak force, though. So unless it gets caught in a planet's gravity or an asteroid or comet's gravity, it's just going to keep going. But it'd be a neat, fun experiment. You know, add a little transmitter to it and see how it's doing. You know what I mean? Simple. Ask that guy with all the satellites to to throw a baseball out in space for us. All right, so all right, so yeah, so now we have some alternating effects here with the gravity bubble. Okay, and now here I want to say again what I think is happening here. Is I got these lines drawn, this gravity bubble. This is actually just the space atmosphere, the space air getting stretched. That's all this is. the light blue lines that I'm using to describe my gravity bubbles is just the space air getting stretched, the space atmosphere. It's stretching it out. The space atmosphere, it allows for it, but also it wants to get back to where it was at. I said that before with like the rubber band. A rubber band allows you to stretch it, but it also wants to get back where it's at. You know, it's got, when you stretch a rubber band and it's trying to pull itself back into its comfortable zone. So with in any object that has mass, it's got a gravity bubble. It's got its own gravity. So that means, in my guess, that it's creating, it's pushing the atmosphere out. It's stretching it out like a rubber band. Because the atmosphere has to be, can't be broken, but it's also trying to regain its ground. So here we are, and I'm getting way off channel here. Doesn't take long. Doesn't take long to get off base. This is why having a team to build a show like this would be awesome. But as it is, it just is what it is. So we're looking at a little bit different pattern here of gravity bubble. Okay, and you wonder why some asteroids, and I know this is on your top wondering list, is why aren't all asteroids perfectly round? Well, this could be why. It could be as simple as this. You have an object with greater mass that's got a bigger gravity bubble, and then you got objects with smaller mass that get stuck to it, so you got bumps and dingers and this and that and the other. So that's why not everything is perfectly round. It's crazy to say that, and I don't know if I'm right about it. You can let me know if I'm wrong about that one too. But the fact of the matter is now we have, and I don't think I drew these lines in accordance with how big they actually should be. This, we may be stretching these things way more because now there are 3 items, and it's a math question on how much mass is involved and how much pressure is being applied to the space atmosphere. How much it's being stretched. So that's a thing, and I keep getting off base here. I want to keep going with this. Okay, so I'll just change gears totally. So originally I wanted to, I mentioned in my first video that the speed of light is just not fast enough. We have to find a faster way. We just have to. It's not a question. It's a need. We need to find a faster way. That's why I want people to get involved. I don't have the answers. I want to help find them. We need to find a faster way. Has to happen. And it has to be possible. Has to be. Because I won't settle for less. Just imagine like you're a race car driver, and you have to win. You need that extra mile per hour. Ain't having it. For you to win, you need it. So what do? You get with your engineers. They figure stuff out over the course of time, and they find a way to get you that extra mile per hour. It's awesome. You know, we're kind of getting back to Darwin, and I hate to say that. For those who don't know about Darwin, uh, he's kind of, I think he was the guy who said if we needed something to happen, we would eventually get it. Um, a lot of disagreements with that, but I think he was more trying to explain about evolution and how animals are different from each other and so on. But we need to find a faster way than speed of light. You know, so one question that I always thought of is, you know, they had built these accelerators that they smash pieces of or atoms or something, particles into each other, and they get these particles moving so fast that they're near speed of light moving. Okay, so they're near speed of light moving, and when they collide, there's my question. Now, if nothing can move faster than the speed of light, what's happening right there? You got this object going here and this object going here. That's faster than the speed of light. That's double the speed of light. That's double the speed of light. Right there is proof that we can move faster than the speed of light. Well, and it should count, because if this is moving near the speed of light and this is not moving, that's a speed of light crash, bump. That's a speed of light bump. But this one isn't just stopped. This one is also going near the speed of light at the same speed as this one, just in the opposite direction, and they hit each other. That does not mean that the fastest speed in the world is 186,000 miles an hour. Or second, sorry, an hour, second. 186,000 miles, point whatever, per second. That's a much bigger collision than that. So that always had me questioning this speed of light Crayola. So that's my main thing, is I want to figure out a way, or I'd like to help figure out a way where not just to prove that the speed of light isn't the fastest source of information transfer, but maybe even build some stuff to access our ability to use a speed faster than light. And it's necessary. I mean, come on, man. Think about it. I'm getting a little angry here. And I got into this in my last video. It's like, if we are going to take our civilization and society seriously, we got to get rid of this dumb speed limit. We've done the math. How long is it going to take? You know? By the time we send a message to wherever and wait for a return, none of us may be here to respond. That is not acceptable. Okay, it's just not acceptable. We have to reach out further than that. We have to find a way. We have to work together, and that's what I'm trying to do here, is work together to find a way to at least communicate faster than the speed of light. Okay. On this planet, it doesn't really matter. You know, we got cell phones, whatever, instantaneous picture, video talking across the world. Instantaneous. It's not necessary down on our planet. You know, it's just not. But, and, you know, some of the things that I'm going to reach out there. Some of the things that we could do if we could understand that things can move faster than light is, number one, I think it has a lot to do with learning more about how gravity works. Okay? Because I believe personally that we will be able to access these tendons of these gravity bubbles. Okay? We'll be able to access these tendons. A little pluck here, a little push there, and we'll be able to do stuff that we weren't able to do before. Let me see here. What's an example? Now I'd have to think about this for a couple of days to come up with a good example. Just off the cuff. Well, just off the cuff, if we could learn how to manipulate these gravity bubbles, or the tendons of the gravity bubbles a little bit, maybe, just maybe, we could pack that shake. We could shake the tendon, but pack that shake with information. You know, pack it. And that tendon goes way out. You know, so in our situation here, and I know this is getting deep. I know I'm getting deep, but you got to wade into it if you're going to figure anything out. All right, so, all right. So let's say we got planet Earth here, okay? And then the sun's back there, and like, let's say Jupiter's over here, and Neptune is out here, and it's pretty big, okay? Now, we all know that each of these has its own gravity bubbles, okay? Magnetospheres, they call them, okay? And some are way bigger than others, you know, but they're all very big, blah, blah. And then, I'm just going to use a little bit different color here to kind of give you an idea. The sun, okay? I'm going to use orange just in this thing to represent the suns, okay? So the sun encompasses everything, okay? Sun's got it to there, sun's got it to there, sun's got it to there, sun's got it further out than that. So here's and this is where I'm going to catch all kinds of grief. If we can learn to shake these gravity tendons, okay? If we can learn to shake these gravity tendons, we can connect either through our magnetosphere to the sun's magnetosphere, which is connected to us. And most of you, I'm just going to keep going. Connect to the sun's magnetosphere tendons, and we have to make sure that we're grabbing the right ones. Basically do a relay. Well, and if we have to jump off of Jupiter, off to there, we can contact Voyager A, you know, way out yonder. Possibly, if it had the right equipment, or if we could make it work in way less time than sending a radio signal. Way less time. I know. So this is what it looks like to take a monster step. You lift your foot up and you step. So that's what I just did here. Taking a monster step. But I got a feeling that I'm right here. I got a feeling. Okay, well, I think I'm not done, but I think I'm done for today. So this video is 25 minutes, whatever. And this one here, all right, and this is my question on this one. And here's where, you know, I imagine after this video I'm going to be burned at the stake. But, you know, if you don't ask the big questions, you don't get the big answers. Okay, so this one here, let me see. Are gravity tendons possible? Yeah, are gravity, are gravity, oops, I can't spell, tendons possible? It's a kind of a two-parter. Are gravity tendons possible, number one, and number two, it's more, I'm going to make it more of a statement. We need to access them. I guess the question could be there. The legit question, and truly legit, is we need to start figuring out a way how to access them. I mean, we know they exist. We see them in the aurora borealis. We see them on other planets and their auroras. We know they're there. We need to be able to access them. Okay, that's going to be a key thing. Now, I'm pretty sure there's probably other people already trying to work on this. So maybe we could add to their work and help them out some way. All right. Big questions, big leaps and bounds today. Even though I'm still here on planet Earth, and probably just ruin my reputation. You know, you gotta have a reputation before you ruin it. It's that simple. All right, folks. See you later. I'll be back again.